Let's solve Unit 5 System Software and Operating System questions. The head of a moving head disk with 200 tracks numbered 0 to 199 has just finished a request at track 125 and currently serving a request at track 143. The queue of request is given in FIFO order as 86, 147, 91, 177, 94, 150, 102, 175 and 130. What will be the total number of head movements required to satisfy these requests for scan algorithm? What is scan algorithm? The disk arm starts at one end of the disk and moves towards the other end, servicing request as it reaches each cylinder until it gets to the other end of the disk. So it will start from one end and move towards the other end. At the other end, the direction of head movement is reversed and servicing continues. Here they have given a clue like it has just completed a request at track 125 and now it is serving a request at track 143. What does this mean? It says the disk arm is moving in this direction. So you have to start satisfying the request in this direction. That is why they have given it has completed 125 and it is currently serving 143. Now the queue of request is given. We will arrange it in ascending order 86, 91, 94, 102, 130. These are before 143 and after 143 we have 147, 150, 175 and 177 and the end is 199. Now currently the head is serving a request at 143. The movement is towards this direction. So after 143 it will move to 147. After 147 it will move to 150. After 150 it will move to 175 and after 175 it will move to 177. Regarding scan algorithm, it will reach the other end, which means from 177 it will travel to 199. So we have to count this movement also. From 199 we have to take the second point. The direction of head movement is reversed and servicing continues. So where is the first request in the reverse direction? It is in 130. So from 199 it will start serving 130. After 130 we have 102. After 102 we have 94, then 91, then 86. So let's calculate the difference. 147 minus 143 is 4. Difference between 150 and 147 is 3. Then 175 and 150 is 25. Then 177 and 175 the difference is 2. 199 minus 177 the difference is 22. 130 and 199 the difference is 69. 102 and 130 it is 28. 94 to 102 it is 8, then the difference is 3 here, then it is 5 here. Now you have to add up all these. So 25 and 5 will give 30, 28 and 2 will give 30, 22 and 8 will give 30, 4, 3 and 3 will give 10, then we have 69 here. So altogether 30 plus 30 plus 30 plus 10 it is 100. 100 plus 69 is 169. So totally there are 169 head movements. Option number 2, 169 cylinders will be the right answer. Next question. Given as 4 GB, approximately 4.3 into 10 power 9 bytes of virtual space and typical page size of 4 KB. And each page table entry is 5 bytes. How many virtual pages would this imply? And what is the size of the whole page table? So there are two questions. We have to find the virtual pages count as well as the page table size. Now regarding the official answer key, this question is declared as dropped. It means no key is declared. So let's take the detail from the question. Virtual space is equal to 4 GB. Page size is equal to 4 KB. Each page table entry is equal to 5 bytes. you have to convert this into bytes. 4 GB virtual space can be written as 4 into 1 GB. So 1 GB is equal to 2 power 30. 2 power 10 is 1 KB, 2 power 20 is 1 MB and 2 power 30 is 1 GB. So 4 into 2 power 30, 4 can be written as 2 power 2 into 2 power 30, which will give altogether 2 power 32 bytes. This is the 4 GB space. And next, the page size, that is also in the form of KB. 4 KB can be written as 4 into 1 KB. 1 KB is 2 power 10. So 2 power 2 into 2 power 10, this will give 2 power 12. This is also in the form of bytes now. Number of pages will be equivalent to virtual space divided by the page size. We can just use 2 power 32 divided by 2 power 12, which makes 2 power 32 minus 12, which is equal to 2 power 20. So number of pages will be 2 power 20. So total page table size is equal to the number of pages into the bytes per each page table entry. So number of pages, it is 2 power 20 bytes into what is each page table entry? It is 5 bytes. So 2 power 20 into 5. The number of pages is 2 power 20. 2 power 20 can be written as 2 power 10 into 2 power 10, which is equal to 2 power 10 is actually 1 KB, which means it is 1024 bytes. So for this 2 power 10, I am writing 1024 into, for this 2 power 10, I am writing 1024. 1024 into 1024 will give 1048576 bytes. Then we'll calculate for the page table size 2 power 20 into 5. So 2 power 20 we have 1048576 into 5. This will give a value of 5242880. This is approximately 5 MB actually, because here the 5 can be kept like this and 2 power 20 is actually 1 MB. So 5 into 1 MB is 5 MB. Now this is how we do the normal calculation, but there is an alternate way to do this using the details given in the question. So they have given virtual space 4 GB is equal to 4.3 into 10 power 9 bytes. So we have seen in 2 power form here. Now we will see in 10 power form here as given in the question. This is how you have to calculate the calculation for this question. So now the page size is given as 4 KB. So what is 1 KB is equal to, we have 10 to the power 3. 1 MB is equal to 10 to the power 6. 1 GB is equal to 10 to the power 9. This is why they have mentioned this to be 10 to the power 9 in 4 GB. 4 KB can be written as 4 into 10 to the power 3 bytes. So now how will you calculate the number of pages? The number of pages will be equal to the virtual space divided by the page size. This will be 4.3 into 10 to the power 9 divided by 4 into 10 to the power 3. So 4.3 divided by 4 will give you 1.075 into, when I take 10 to the power 3 to the numerator, it will be 10 to the power 9 minus 3, which is equal to 1.075 into 10 to the power 6. 10 to the power 6 means you will have 1 and 6 zeros together. This will be 1075. So 3 zeros will go for this decimal point and additionally there will be 3 zeros. So this will be the answer. Actually 1075 and there should be 000 and not 00. This is the problem with the first option. As per this question, number of virtual pages will be 1075 and 000. Then regarding page table size, so we have the number of pages into each page table entry. The number of pages you can keep it as 1.075 into 10 to the power 6. Then the entry will be 5 bytes as per the question. Let's take this to be 5 only, because 5 point something it will give. 10 to the power 6 is actually 1 MB. So this will be approximately equivalent to 5 MB. For this question, you have to use this method. because they have explicitly given in 10 pass. But usually we will solve the problem in this method using 2 par. Sometimes they will stop the answer in the options with 2 pass or 10 pass. At that time you need not go with the complete number. But if they ask you in terms of bytes with a complete number, you have to calculate this way and bring it to this form. Since there is no key, I'll just mark the answer alone here. So page table size will be approximately equivalent to 5 MB. So this will be the answer to the question. If you multiply 5 into 1.075, you will get 5.375 into 10 to the power 6. So this will be like 5375000. Next question. In Linux, where is the user password stored? A simple example of signature-based detection is scanning network packets for the string in the path etc password targeted for a unique system. So usually signature-based detection is what they mean as password in Linux context. So for a Unix system, they usually store in etc password spelled as PASSWD. This is the actual place where the user password is stored. So option number 3 will be the right answer. Next question. The average time required to search a storage location in memory and obtain its contents. So there are two processes here. One is to search the storage location in the memory and the other is to obtain its contents. So there are 4 times given here. Reading time doesn't apply to the context of OS or computer system architecture. So we can easily rule out option number 4. And regarding this question, some will place it in unit 2 and I have placed it in unit 5. It is because of the relevancy of the options. Access time is the interval between the beginning of one storage device access and the beginning of the subsequent access. Subsequent means another access. So when will you go for the next access? Only when you have completed the access to the first item, you will go to the access of the second item. So this denotes the complete process of searching and obtaining the content. So access time is equal to latency plus transfer time. So what is latency? The cost of traveling to the appropriate location on the device and making preparations to access it. So this part. And obtaining its contents is transferring it to the place where you want to use it. So this is the transfer time. From this we can say the average time to search as well as to obtain content will be option number 1, access time. One half of the statement, searching the location, will apply to latency time and the next half is not there. So we are ruling out option number 2. And response time is not about searching something. Response time is the time from the submission of a request until the first response is produced. It is the time it takes to start responding, not the time it takes to output the response. This is not relevant to the statement given in the question, so we are ruling out even response time. Next question. Which of the following statements are not correct about NUMA? So this question can also be placed in computer system architecture. So let's see about NUMA. Multiprocessing can cause a system to change its memory access model from uniform memory access UMA to non-uniform memory access called NUMA. So this is what we are calling it as NUMA. So NUMA machines have 3 characteristics. There is a single address space visible to all CPUs. Access to remote memory is via load and store instructions. Access to remote memory is slower than access to local memory. So take this to be a local memory for node 0 and this is a remote memory for node 0 alone. So access to the local memory will be fast. But when I have to access the memory of node 1, which is a remote memory for node 0, it will obviously take more time for it. So that's why they say access to remote memory is slower. When I want to access a memory that is not local to my machine, it will definitely be slower than accessing the memory of my machine. So from this, load and store instructions are used to access remote memory. From point 2, we can say A is true. So they are asking about not correct. Coming to B. There is a single address space visible to all CPU. This is also right. So A and B are true. Any option that includes A and B will be ruled out. So three options are ruled out. From this we can mark option 4 will be the right answer, which means both are wrong statements. So now the C statement. Access to local memory is slower than access to remote memory, which is contradicting this statement. So as per point number 3, it is faster than access to remote memory. So this is wrong. We can mark C to be false. Next D. When the access time to remote memory is hidden, the system is called NUMA. Let's see the relevant statements. When the access time to remote memory is not hidden because there is no caching, the system is called NUMA, that is non-cache coherent NUMA. So since there is no caching, they say when the access time is not hidden. But here the statement is they have given as is hidden. So whenever it is not hidden, we call it as NUMA. So D is false. The actual statement should be not hidden. So we are marking it wrong. In NUMA, cache coherence are present as per E statement. When the caches are coherent, the system is called NUMA, that is cache coherent NUMA. So NC is non-cache coherent, CC is cache coherent. E statement is true. So A, B, E are true, C and D are false. As per this question, option number 4 will be the right answer. Next question, indexed or grouped allocation is useful as. Indexed allocation supports direct access without suffering from external fragmentation, because any free block on the disk can satisfy a request for more space, so it does suffer from wasted space. But it does not suffer from external fragmentation. I'll let you know what it is later. With indexed allocation, an entire index block must be allocated even if only 1 or 2 pointers will be non-null. If the index block is already in memory, then the access can be made directly. However, keeping the index block in memory requires considerable space. If this memory space is not available, then we may have to read the first index block and then the desired data block. So in continuous allocation, what happens is we continuously allocate the files. So it starts from 0 index and the length is 2. So 0 and 1 is for count file. Then if you take F file, it starts from 6 and the length is 2. So only 6 and 7 will be allocated for F. We have indexed allocation here. In indexed allocation, what happens is there is a file called Jeep and they say it starts in index block 19. So it starts here. Now in the index part, they will mention where are the other parts of the file present. So the other parts are index 9, index 16, index 1, index 10, index 25, and the remaining will be kept as null. So that is -1. So here if you take 9 is there, then you have 16, then you have 1, then you have 10. This is how index allocation will be there. So if the index block is already in memory, then the access can be made directly, and keeping the index block in memory will require considerable space. See, the starting index is alone given here. The index block 19 has all the details of the file. But here the starting index and the length of the file is given in this directory. But here only the index block number is given. If you get into the index block, the related index will be present here. So you need space to store this as well as this. That's what they say. It requires considerable space. Some systems combine continuous allocation with indexed allocation by using contiguous allocation for small files up to 3 or 4 blocks and automatically switching to an indexed allocation if the file grows large. So some system combine both these strategy. How do they do? When it is a small file, they go for contiguous allocation, and when it is for a large file, they automatically switch to indexed allocation. This is how it happens. So now let me tell you what is external fragmentation. External fragmentation exists when there is enough total memory space to satisfy a request, but the available spaces are not continuous. So the storage is fragmented into large number of small holes. So regarding index, there is no problem of external fragmentation because it is going to store only the index locations in the index block. Here they say external fragmentation is the storage will be fragmented into large number of small holes. Though there are spaces, the spaces will not be continuous. Say for example 8, 9, 10, 11 is available, then 17, 18 is available. So 6 spaces are available here. But when you want to store a file called A with length 6, where will you allocate here? Because at a stretch you have only 4. So what it will do is, it will store here for 2 and here for 4. So this 2 and 4 will make up together a length of 6. So this is external fragmentation, and in index allocation we don't have the problem of external fragmentation because it is going to store only the index in the index block. So now we will see the options. It supports both sequential and direct access. Yes, it can access sequentially as well as it can access directly if the index block is already available in the memory. So both are possible. Option A is fine. Entire block is available for data. Yes, it is available. With index allocation, an entire block must be allocated here. So this is also fine. It does not require lots of space for keeping pointers. It requires space for pointers. This part has to be stored. Only then we can collectively know where the file contents are present. So in that case, it requires considerable space. So when they say it does not require, it is actually wrong. It actually requires lots of space is the right statement. Then there is no external fragmentation. This is true with regard to indexed allocation. They say it is not suffering from external fragmentation. So external fragmentation is when you don't have continuous storage, you have to fragment the path. So that will not happen in case of indexed allocation. So D is also right. Option A, B and D are correct. So here the question is, this allocation is useful as it supports both the access, as the entire block is available for data, as there is no external fragmentation. So everything is going to be a reason except C. Option number 4, A, B and D only will be the right answer. Next question, which of the following statements are correct? Each process has a segment of code called a critical section, in which the process may be changing common variables, updating a table, writing a file and so on. So every process has to request permission to enter the critical section. A process always checks state of currently executing process to enter critical schema. They say it must request permission to enter critical section, but here the story is about checking state. That too, it will always check state, which is actually contradicting the statement. So A will not be right. A mutex lock has a boolean variable available whose value indicates if the lock is available or not. Since it's a boolean variable, it should either be 0 or 1. The main disadvantage is that it requires busy waiting. This type of mutex lock is also called spin lock because the process spins while waiting for the lock to become available. So spin locks uses busy waiting is perfectly true. B is true. But we know A is not true, so 1 will be ruled out here. What is busy waiting? A process or a task waits and constantly checks for a condition to be satisfied before proceeding with its execution. Periodically testing a variable until some value appears is known as busy waiting. They say it constantly checks for a condition. Periodically means after some period of time it is checking. So C is also wrong in case of busy waiting. Constant means it continuously keeps on checking. It always checks. So in that case they say, then critical region is a part of program where shared memory is kept. So what is the critical section? It may be changing common variables, updating a table, writing a file and so on. So when shared memory is kept, only then it has to ask permission to update or ask permission to change some variable value or ask permission to write a file. So if that memory is not shared, it will automatically update itself. Only when there is shared memory it has to seek permission. So in that case critical region is a part of program where shared memory is kept is perfectly true. So since C is also wrong, we can rule out option 2, and since D is right, we can go with option number 3, B and D only. Option 3 will be the right answer. So from this we can conclude E is definitely false. But why it is false? The printer daemon periodically checks to see if there are any files to be printed. But what has been given in E statement? The printer daemon continuously checks to see if there are any file to be printed. This is not the case for printer daemon. So this is continuous testing and this is periodical checking. So the words are exchanged in C and E, that's why they are wrong. So in this case, we can mark option 4 also to be wrong. Next question, match list 1 with list 2. So we know least recently used. LRU is a page replacement algorithm. Least recently used means it has not been used recently. So a page that has not been referenced for longest time is replaced. This will be perfectly apt for LRU. Which option has A mapping to 2? The only option will be option number 2. Now what is B? Demand cleaning. Demand cleaning means a page is written to the secondary memory only when it has been selected for replacement. So B will be mapping to 1. What is long-term scheduling and what is medium-term scheduling? The decision to add to the pool of processes to be executed is given in 4. The decision to add to the number of processes that are partially or fully in main memory is given in 3. Regarding the words, medium is something that is going to happen in a short time. Long term is it will take a long time to happen. A process is partially or fully in memory and the decision to add to the number of processes can be medium term scheduling. So in that way D is mapping to 3. And when it comes to long term scheduling, the decision to add to the pool of processes to be executed. You have a set of processes to be executed stating P1 and P2 and already some processes are in memory stating P3 and P4. So these are already in execution. These are waiting to get into execution. So here adding to the pool of resources, if I have a process P5, adding here will be long term because I have to get the memory, then I have to go for execution is this part. But adding to the number of processes is adding in this part that are partially or fully in the main memory. It means it is executing. So adding to this should be medium term scheduling. When I am adding something to what is already in the main memory, it is going to be executed very soon. When I am going to add something to the pool of resources, it has to get the chance to execute. So here the wait is long and here the wait is short. So C will be mapping to 4. So from this we can say option 2 will be the right answer. Next question. Arrange the following levels of interrupt protection within the Linux kernel in the order of increasing priority. So let's see a diagram. It's about the interrupt protection levels and the increasing priority is from bottom to top. So which is having the least priority user mode program. They are preemptible. Preempting is allowing another one to execute when something is getting executed. Non-preempting means until the process that is executing is going to be completed, it will never allow others to interfere. So user mode programs take the least priority. Next, kernel system service routines take the next priority. So here user mode programs A will be first, then we have kernel system service routines C, they are also preemptible. Then we have bottom of interrupt handlers B, then we have top of interrupt handlers D. A, C, B, D. Option number 2 will be the right answer. So when you find this is A as the starting one, you can rule out 4. When you find it is A and C, you can rule out 1. When you find it is A, C and D, you can rule out even 3. Next question. Given below are two statements. A thread is a dispatchable unit of work that does not execute sequentially and is non-interruptible. This word is more than enough to say that this statement is wrong. If you take a particular process, it will create many threads. Take a process like this. There are 3 threads. Let me mark it like this. When this is executing and when there is a need, this thread will get executed. It does not mean it won't be interrupted. We cannot say like that. So when you find that it is non-interruptible, you can easily say this statement is false. Now we'll see the exact statement. Thread is a dispatchable unit of work that executes sequentially. So this word is also wrong and is interruptible, and this is also wrong. Next statement. It is not possible to alter the behavior of a thread by altering its context when thread is suspended. The set of register values and other volatile data that defines the execution state of a thread, they make the thread context. Here they say it is not possible to alter the behavior by altering the context. The context is having some register values and the execution state of a thread. A thread can be prevented from executing for an indefinite period of time if it becomes suspended. Suspending the running thread will cause a context switch to another thread in ready state immediately. If one thread is suspended, the running thread is suspended means automatically there will be a context switch to another thread which is waiting in the ready state. So this will happen immediately once a thread becomes suspended. The suspended thread is not executed until explicitly resumed with the appropriate function. So here they say suspended thread will never execute, but it will cause a context switch to another thread. Switching the CPU from one thread to another involves suspending the current thread, saving its state, and then restoring the state of the thread being switched to. There are 3 things happening. One is the current thread will be suspended, the current thread's state will be saved in the appropriate registers, and then it will restore the state of the thread that it is being switched to. When there is an option to save the state, definitely there will be an option to restore the state later. They say the suspended thread can be explicitly resumed. At that time, it can restore the state. You can restore the state of a thread only when you save that particular state. So there is an option to alter the context when the thread is suspended. So we can save the state, which means it can alter the behavior of the thread. So take T1 and T2. T1 is suspended and it has a saved state, and T2 is now executing or running. In this case, it is possible to alter the behavior of the thread by altering its context when the thread is suspended. The behavior of T2 thread ready to execute. So this is also changing the context. Altering means changing the context. So when they say it is not possible, this is definitely false. It is possible to do that. Since both the statements are wrong, option number 2, both statement 1 and statement 2 are incorrect will be the right answer. With this, we are completing Unit 5 questions.